Welcome to Calculus Applied. I'm Juliana Belding, a math professor at Boston College, and this is Peter Garfield, a math professor at UC Santa Barbara. Peter and I met teaching math at Harvard University. We regularly taught together, and our students often asked, like you may be now, how is calculus really used outside of mathematics?
While you can find some applied problems in the back of a textbook chapter, we wanted a more satisfying answer. So we decided to ask people who actually use calculus in their work to help us answer this question.
So we interviewed economists and biomathematicians, environmental scientists and applied mathematicians, physicists and statisticians.
In this course, you'll hear their stories and have a chance to try problems like the ones that they tackle, using tools from single variable calculus.
So what is it about calculus that is so useful? One of my favorite quotes about math is from the 18th century mathematician, Joseph Fourier. He said, "Mathematics compares the most diverse phenomenon and discovers the secret analogies that unite them." Calculus is full of these secret analogies. The idea of change, of accumulation, of approximation are everywhere, from price and demand in economics, to population growth and decline, to Einstein's mass energy equivalence. Calculus gives a qualitative and quantitative way to describe these phenomena through derivatives, integrals, and limits.
As we move through this course, one thing you'll also notice is that we talk a lot about models. We'll be looking at situations in which calculus, and math in general, helps people create and analyze models that capture what's going on and allows us to explain or make predictions. Here's a preview.
We'll talk to biomathematician Wes Kane about understanding sudden changes in the environment through differential equations, which are derivative models. Through these models, we'll look at how populations change with time, or food resources, predators, and competition.
We'll talk to Margot Levine, an applied mathematician who studies medical imaging. She'll share a model for X-rays passing through the body, which involves integration, and explain how X-rays are different than CT scans.
We'll talk to physicist Mboyo Esole and analyze Einstein's famous energy and mass equation using Taylor approximation.
We'll model the interplay of price and demand for subway rides using average and instantaneous rates of change, and talk to economist Kiran Gajwani about some factors at play in this model.
While the models we see in this course will probably be new to you, modeling using calculus may be a familiar idea if you've taken a calculus course.
For example, suppose you throw a ball in the air. We can make a mathematical model of this physical situation. In part, this projectile motion was a motivating example for the very invention of calculus. If we describe the height of the ball in feet after t seconds by the equation h of t equals 5 plus 40t minus 16t squared feet, what is this model telling us? The 5 is the initial height in feet, the height at time t equals 0. The derivative can help us with the meaning of the other terms. The velocity is the derivative of the height. So v equals h prime of t equals 40 minus 32t feet per second. So the velocity at time t equals 0 is 40, the initial velocity. The second derivative gives us the acceleration at time t. This is the derivative of the velocity and the second derivative of the height, and it's negative 32 feet per second squared. Notice that the acceleration is constant. In fact, you might recognize it. The acceleration is negative 32 feet per second squared. This is g, the acceleration due to gravity at the Earth's surface. So each of the terms in our model for h of t has a purpose, and calculus can explain the role of each term.
And not only that, but calculus explains why this is the right model. If we assume that the acceleration is the constant of gravity, then by integrating this twice, we get the exact model for the height of the ball.
So that was fast, because we hope this was a familiar example, but we want to reassure you that we'll take our time with new models that we encounter. And one thing we'll be doing with all of our models is looking at their uses and their limitations. For example, we can use this projectile motion model to answer questions like how high the ball will go, or what time the ball will land, and how fast it will be going at that moment.
We can also see that we've made many assumptions in our model. We've assumed the acceleration of the ball is that of Earth, but we've also assumed that the ball isn't slowed by friction or affected by a gusty wind. Assumptions are part of every model and give us insight into those limitations that you mentioned. We'll see in this course how calculus appears in building and understanding much more complicated models.
The idea of altering a model to better fit a real-life situation is another key idea that will come up often in this course.
Welcome again to Calculus Applied.